Morning all. Today we discuss some applications of operational amplifier. In the previous sessions, we discussed mainly inverting and non-inverting amplifiers using op-amp. Here we discuss the applications of these amplifier, inverting and non-inverting amplifier. In the introduction, we have mentioned that an operational amplifier can be used to perform mathematical operations such as summation, subtraction, integration, differentiation, etc. Today we discuss some of the mathematical operations done by the op-amp will be discussed. First one is the summing amplifiers. By the name, it is clear that a summing amplifier must be used to find sum. So here we use an inverted operational amplifier for the summation purpose. So a summing amplifier is an inverted op-amp that can be accept two or more input. The output voltage of a summing amplifier is proportional to the negative of the algebraic sum of the input voltages. Here we use the inverted op-amp. So the output must be proportional to the negative. The negative indicates only that the output is out of phase with the input. Hence we give the name summing, as the output voltage is proportional to the algebraic sum of the input voltage. Consider the figure. Look at the figure. When we look at the figure, it is clear that this op-amp is operating in inverting mode because the non-inverting terminal is grounded and RF resistor is connected to the inverting terminal and to the inverting terminal. There is 3 different resistors are connected, that are R1, R2, R3. Here 3 resistors are connected into the inverting terminal. But we can use more than 3. We can use any number of inputs, any number of resistance at the inverting terminal. If you want to sum 10 voltages, 10 quantities, then we must use 10 resistance R1 to R10. Okay. Here in this figure, this summing amplifier is used to add 3 inputs. Let the voltages are V1, V2 and V3. Okay. These voltages produce a current I1, I2, I3. The corresponding resistors R1, R2 and R3. Okay. That is, we apply the input voltage V1, V2, V3. So the current flowing through the corresponding resistors are denoted as I1, I2 and I3. Okay. And using the concept of infinite impedance and the virtual ground, you can see that the inverting input of the op-amp is at virtual ground and there is no current into the input of the op-amp. Okay. We know that this terminal, the positive terminal, is at ground and the impedance between the negative terminal and positive terminal, the impedance between the 2 terminals of the op-amp is very high. So the voltage drop across this input must be 0. So this ground must appear at the negative input terminal. So we called it as virtual ground. The virtual ground is discussed in the previous sessions. So due to the virtual ground and the high input impedance at the input, there is no current flowing in this direction. There is no current flowing into the op-amp. Okay. Is it clear? Now we're going to show that the circuit sum the inputs V1, V2 and V3. When we applying the inputs V1, V2, V3, we have mentioned that the currents corresponding resistors must be I1, I2 and I3. So using the Kirchhoff's current law, the current at the point A, the current at the node A must be equal to what? When we are applying the Kirchhoff law at the point A, the current meeting at the junction must be equal to the current leaving at the junction. So the current meeting at the junction is I1 plus I2 plus I3, and the current leaving at A is IF. So we write IF is equal to I1 plus I2 plus I3. Okay. And the output voltage. The output voltage V out is equal to what? V out is equal to minus IFRF, isn't it? The minus comes from the inversion. Okay. Or it can be obtained from the Kirchhoff's second law, as we know that the current through the RF resistor must be equal to the voltage across RF divided by RF. The voltage across RF, IF is flowing in this direction. Okay. So the voltage drop across RF is equal to 0 minus V out. It is the voltage across RF. V voltage across RF is equal to this quantity, 0 minus V out. Then the current through this one must be equal to 0 minus V out. 0 minus V out is equal to minus V out divided by RF. So V out is equal to minus IF RF. Is it clear? Okay. Then in the place of IF, we substitute I1 plus I2 plus I3. Okay. We substitute the value of IF as I1 plus I2 plus I3. So we can write it is equal to I1 must be equal to what? I1 must be equal to I1. I1 is the current through the resistor R1. Then here the potential is 0. Then the voltage across R1 is V1. Then we can write I1 is equal to V1 divided by R1, and I2 is equal to V2 divided by R2, and I3 is equal to V3 divided by R3. Okay. Substituting the value here, we write V1 divided by R1 plus V2 divided by R2 plus V3 divided by R3 minus RF into V1 by R1 plus V2 by R2 plus V3 by R3. Okay. If R1 is equal to R2 is equal to R3 is equal to R, the three input resistance taken as equal and it is equal to R, then we can write output voltage V out. V out is equal to what? V out is equal to minus RF. If the denominators are same, we can take it outside. Then minus RF divided by minus RF divided by minus RF divided by R, because the three resistors R1, R2, R3 are equal and it is equal to R. Then in brackets V1 plus V2 plus V3. Okay. Thus, the output voltage is proportional to the algebraic sum of input voltages. Look at the figure. Sorry, look at the expression. V out is equal to minus RF by R into V1 plus V2 plus V3. V1 plus V2 plus V3. It represents the sum of input voltages. So V out is proportional to the sum of input voltages, but it is with a product minus RF divided by R. So to get the unity gain, we must take the RF we get in the previous session. We get the expression, of V out, that is equal to minus RF divided by R into V1 plus V2 plus V3. Here the output voltage is proportional to the algebraic sum of input voltages, or V out by input voltage must be equal to minus RF by R. There is a gain. For unity gain, to obtain unity gain, we must take RF is equal to R, isn't it? So when we put all the resistors are equal, or we also take R1 is equal to R3 is equal to R3 is equal to R, then we take also RF is equal to R. Okay, when in the case RF is equal to R, we will express V out is equal to V out is equal to what? Minus of R1, sorry, minus of V1 brackets V1 plus V2 plus V3. So V out is equal to negative of the sum. Okay. Here we write here V out is equal to minus V1 plus V2 plus V3. Okay. Thus, when the gain of the summing amplifier is unity, the output voltage is the algebraic sum of input voltages. The output voltage is now the algebraic sum of the input voltages. If we have to add more voltages, the additional resistance must be given. Okay. Next, we discuss another application, that is averaging amplifier. Averaging amplifier. What is the difference between summing and averaging? Is there a connection between summation and averaging? In averaging, we have to sum all the data and divide it by number of data, isn't it? So, an averaging amplifier must be with a summing amplifier. Okay, an averaging amplifier must consist of a summing amplifier. Okay, so first we consider the previous case that we have three input voltages V1, V2, V3. In the summation, we get the output V1 plus V2 plus V3. As there is three inputs, if we divide it by 3, it must be the average voltage. I written this quantity V average is equal to 1 by 3 into V1 plus V2 plus V3. Then we compare it with the expression of summing amplifier in the initial stages, that is V out is equal to minus of RF divided by R into V1 plus V2 plus V3. Okay, so if we take the RF divided by R is equal to some ratio, or that must be equal to 1 by n, if n is equal to the number of input voltages. Then we can use the same circuit of summing amplifier but with different set of values for resistors. Okay, then here we write RF by R is equal to 1 by n, or from that we can write R must be equal to n into RF. Okay, here it is the circuit diagram of the summing amplifier. So the conditions to convert an averaging amplifier to, so the condition for a summing amplifier to be worked as an averaging amplifier, all the input resistance R1, R2, R3, etc. input resistors must be in equal, but the value of the input resistance must satisfy the condition, that is the ratio of input resistors to the feedback resistor equal to the number of input circuits. That is, the condition is RF by R must be equal to, or R divided by R. From here, this condition says that R divided by RF, the ratio of any input resistor to the feedback resistor is equal to what? Equal to the number of input. Okay, if the condition is satisfied, R by RF is equal to N, or the condition is here, R by R is equal to NRF, then a summing amplifier must be operated as averaging amplifier. Here we take the previous case. In the previous case, there is 3 input, V1, V2, V3. As there is 3 input, the value of n must be equal to 3. Then 3 RF must be equal to R1, R2, R3, or the total values 3 RF is equal to these quantities. Then in the output voltage must be equal to V out must be equal to minus 1 by 3 V1 plus V2 plus V3, isn't it? Minus V1 plus V2 plus V3 divided by 3. So the average of the output is average of the input is obtained as the output. So if there are n input, NRF must be equal to R1 equal to R2 is equal to R3 up to Rn. Then the output voltage must be equal to V out is equal to minus, here the output voltage is plus etc. Here V out must be equal to minus of V1 plus V2 plus etc. up to Vn divided by n, here plus etc. Okay. So the V out is equal to the average, but with a negative sign. Okay. Negative sign indicates the phase reversal. Now we go to subtract. Okay. We know that the subtraction can be done using inverted addition. What does mean? Consider an expression that is C is equal to A minus B. We have to perform A minus B. A minus B. So we can done it using A plus minus B, isn't it? A plus minus B. To perform this quantity, let it be minus B is equal to A plus D. That is D is equal to minus B here. To perform A plus D, we can use a summing amplifier with 2 input. Okay. A summing amplifier with 2 input. Okay. And to obtain this, we must invert the B. Okay. That we have 2 inputs. We have 2 inputs A and B, but we have to obtain A minus B. We have to obtain A minus B. So we must use a summing amplifier and a inverting amplifier with unit gain. So to perform a subtraction, we use 2 op amp Here, the first one, look at the values R1, RF. For the first circuit, R1, RF, they are equal and it is operating in inverting mode. Okay. So it is a unity gain. Which type amplifier? Unity gain inverting. Unity gain inverting amplifier. What is that? Unity gain inverting. Or the output must be, V out must be equal to what? V out must be equal to minus V in. V out is equal to minus V in. Okay. So here we give the input V1. Okay. Here we give the input V1 here. It is a unity gain inverting amplifier. So at the output of this amplifier, we get minus V1 as the output. And we consider the second amplifier. Look at here. It is RF. It is input resistor. It is termed as R2 and R3. There are two input resistors R2 and R3. It is connected to negative and positive is grounded. So it is a summing amplifier. One of the input of the summing amplifier is V2 and the other is minus V1. Here the values of R2 and RF and R3 both are R1 is equal to, R2 is equal to R3, that is equal to RF. So the gain of the summing amplifier must be equal to what? It must be equal to 1, or the output of the summing amplifier must be equal to V out of the summing amplifier must be equal to what? It must be minus of, okay, minus of as the ratio of these are same. So the negative of the voltage at, I write the voltage at R2 plus the voltage at R3, isn't it? Okay. So when we give the values here, VR2 is equal to what? VR2 is equal to minus V1 and VR3 is equal to V2. Then minus V1 plus V2 with a negative sign. Then it must be equal to V1 minus V2. So here we use summing amplifier with a unity gain amplifier to obtain the subtraction. Here I write the output of minus of minus V1 plus V2, or that is equal to minus plus, then it is equal to V1 minus V2. It is the subtraction. Okay. The output voltage is equal to V out is equal to minus of V1 plus V2, that is equal to V1 minus V2. So we discuss the summing amplifier, averaging amplifier, and subtracting amplifier. In the next session, we will discuss integrator and differentiator. So I stop here. Thank you.